All right, welcome back. Right, this is part two out of what, seven, if I'm counting this correctly. Now we will go in and start with our analysis of steady flow devices. Right, as with last topic, or as with the last part, if you guys have watched part one, if you haven't watched part one, go watch it now. Right, what I said there is that I think quiz 3 is somewhat going to be a little bit easier, or at the very least a little bit more predictable, because, well, you know what to do. It's just that you're gonna have to do it. Right, so for the lazy ones out there, yeah, this one goes to all of you. Okay, now we will go and first, of course, define what a steady flow device is. And, well, it's just a device that operates under steady flow. That's it, right? So it's a component in a larger thermodynamic system used to carry fluid while at steady flow. Basically, anything wherein the process, or rather the system, is to be treated as steady flow or just open, right? And in this case, there are many categories to steady flow devices, right? This will be the main checklist. Excuse me. This will be the main checklist of topic 5, right? We will go through 1, 2, 3, 4, 5, 6 steady flow devices. We will start off with pipes, nozzles, and diffusers, and of course, those have to be the most basic ones, right? Pipes, right? If you want to define what a pipe is, then go ahead, right? A pipe is basically just anything that is used to carry fluid, right? And in this case, I have to declare that in a pipe, the ideal process is isobaric, right? Excuse me. For some reason, I'm developing like a. It's not a cold, but anyway, right? The ideal process in a pipe is isobaric. What does that mean? If you remember from our discussion last time, is that for an isobaric process there is no steady flow work. This is our way, or rather, this is their way of saying, right? Not my way of, like, but this is the pipe's way of saying that if, right, if this is ideal, then the pipe is not supposed to move. No movement, right? And for all of the types of steady flow devices that we will discuss, I will present in here the first law, right? As I've said last time, you will know that you will always use, right? You will always use the first law, especially in this regard, the one with the delta H, because you're going to be working with open systems. This will always crop up. It's now the time for you to be able to understand which ones you're supposed to cancel, right? And there was a time, like a last week, I think it was, right, when my girlfriend and I were looking at my old, like, files, my student files. And when I was a student of METHER1, right, we found out that my quiz 3 was the highest. And I did remember it to be somewhat enjoyable because, right, whenever you write down the first law, this equation right here, there are 5 terms, right? And well, 5 terms, that's quite a lot, right? So what you're supposed to do next, and what I found enjoyable, was the act of canceling. Canceling, what do you mean canceling, right? Whenever you're writing this down in your solution, there will always be something that you can at the very least cancel. What do you mean? First off, we just said that this ideally is isobaric. So there should be no movement. In that case, there's no work. So you cancel the work. It's now down to 4. Excuse me. It's now down to 4 terms. And usually a pipe, well, you can do anything you want with a pipe, but usually a pipe is not used as a heater or a cooler, right? You're not supposed to set fire to a pipe to heat the fluid inside, right? Or, well, I don't know. I don't control what the manufacturers do, but usually there's no heat transfer as well. That leaves us with this thing, right? Delta Ke plus delta Pe plus delta H. And because of this fact that usually there is no heat transfer, it would only make sense that there is a negligible change in temperature as well. And so why am I saying stuff about temperature? It's because the last time we were talking about temperature, right? It was Joule's experiment, and basically what we said in there was that internal energy U and temperature T were related. right? In fact, that is how we described our internal energy before. The amount of energy that you would associate with hot, right? This is the kind of energy, delta KE is the kind of energy you would expect if something is going quickly, right? Delta PE is the kind of energy you would expect when something is really far away, really on top of a tall building or whatever, right? And there is a delta U that you would experience when something is warm or basically is just has a high temperature. Because there is no heat transfer, it would make sense, right, that your delta U is zero as well. And so now, why am I saying this? It's not here, right? But the thing is, right, your H is equal to U plus PV, right? It's U plus this thing, what we call the flow energy, right? Flow energy. The thing is, now, if we're going to do delta H, well, that will be delta U plus delta of this flow energy right here. So you are canceling this part of the delta H. Excuse me. You will be left with this thing, delta PV. Okay, there's no change in internal energy. You're left with the change in flow energy, and you can rearrange this to become something like this. Okay, now you might notice what's so different with this thing, or what's so important with this thing. Actually, this is just a little aside, right? But our delta notation tells us that the delta of something is just the final something minus the initial something. And you will notice that that will repeat for all of the terms in here. They will always have a KE final minus KE initial, PE final minus PE initial, P2 V2 minus P1 V1. And basically, you can put all of the initials because they all have negative signs. You can put all of them to the other side like this, right? And now, what's going to happen is that let's just say what we already know about KE. KE is defined as 1/2 mass times velocity squared. And then PE is just mgh, or in this case, elevation is now denoted as the letter Z. So, something like this. Now, what we will do, the final magic phrase, is to divide everything by volume. You might now say, okay, which volume? Is it V1 or V2? Now, we're supposed to put in here the assumption that we are doing this for liquids, right? For liquids, aka for any incompressible fluids. So that means that V1 and V2 in this case are just going to be the same. And if you're going to divide everything by volume, what you're going to create in here is a mass over volume. A mass over volume. Cancel. Mass over volume, mass over volume. And then cancel, right? And what's going to happen? All of these mass over volumes, they're going to turn into rho, right? They're going to turn into density. And so you arrive at this. If this is not yet very familiar, this should be, because this is the same thing as one of the most acclaimed or one of the most famous mechanical engineering equations out there, which is, of course, Bernoulli's principle. Right? Bernoulli's principle is simply, right, a restatement of the first law. And you might say, okay, another aside, right, a tangent to the tangent, right? You might say, okay, so which Bernoulli is this, right? This is actually Daniel Bernoulli, this guy, right? He is not the same Bernoulli, I think. He's not the same Bernoulli who has done Bernoulli trials in statistics and probability. Is not the same kind of Bernoulli. He's also not the same Bernoulli in Bernoulli differential equations, in your differential equation. So, but the Bernoullis, they're very acclaimed family because they're all smarty pants, right? They're all mathematicians in there. Apparently, Daniel Bernoulli is the smartest out of the kids, the Bernoulli kids. But sorry to spoil it, this is not actually first discovered by Daniel Bernoulli. The one who discovered it is Mr. Towel, right? The OG, it is Leonhard Euler, right? So this should be Euler's principle, but he already has so many other math things named after him, right? The Euler's number, Euler's formula, another Euler's formula, more formulas, so on and so forth, right? It's all his, But, right? Bernoulli's principle is really just a restatement of the first law. This is how I just want to show you guys that this is indeed just the first law, in a very confined, in a very special manner, right? This basically says that your speed, your elevation, and your pressure are all related, right? If something is going to go up, something else must go down, right? Say, for example, your velocity increases because of the fact that 1/2 rho vel squared plus rho gz plus p is constant. Something else must go down. Maybe the elevation will go down, right? Which makes sense, right? A jet of water is going to only spray up until it can't anymore, right? So it will go down. And then maybe also the pressure decreases, right? You'll learn more about this in your fluid mechanics. This is why the colors changed a little bit. But yeah, I'm not your fluid mechanics professor. I'm just your METHER1 professor. I'm just your thermodynamics professor. So take it as it is. Okay. Now we will go back to pipes. And now I will show you one of the longest, right? I will show you one of the longest, one of the longest problems for topic 5, which is this one, right? Let me blow my nose a little bit. I don't know why I'm suddenly developing like snot. Anyway, air enters a horizontal constant diameter heating duct at steady state, measuring 20 degrees Celsius, 1 bar, and a volumetric flow rate of 0.25 cubic meters per second. It then exits at 50 degrees Celsius, 0.95 bar, through a flow area of 0.04 meters squared. Assume that your K is 1.4, although technically I don't need to say this out loud because you guys should know the K of air. Determine the mass flow rate in kilograms per second, the velocities at the inlet and the exit in meters per second, and the heat transfer in kilowatts. Okay? All right. So let's go through with this, right? Yeah, I actually have it here already, right? So let's just draw the schematic diagram, right? Technically, I will not ask you guys to just draw this for partial points, right? If you don't want to draw this, whatever, right? If you think that you are hot stuff, that you don't need the schematic diagram for you to solve, then go ahead by all means, right? Basta, the only thing that the thing that the schematic diagram can give you is a visual sense of things, right? Because, well, with the way I have my quizzes, I will not be including pictures in that thing, right? The thing is, this gives you a visual, a more visceral kind of thing, a more visceral kind of imagination as to what the device looks like, right? This is horizontal, so there's that. It's constant diameter, so that means that the area of this first part right here, this first state right here, is the area of the second state right here, right? Yeah. So this is area 1, which is equal to your area 2. And right, let's just go ahead and list down everything that we know. Air. So we are talking about air right here. Air enters a horizontal, okay, horizontal, constant diameter heating duct. So constant diameter heating duct. So let's just, well, for the lack of a better, what do you call this? For the lack of a better drawing, let's just draw some fire into this, right? Let's just draw some fire like this, okay? Heating duct at steady state. All right, that is our clue or our go ahead that we should treat this as steady flow. The thing is though, with all of the problems that are going to come after this, right? You should always think about this as being in steady flow unless I say so, which I probably won't say so because everything in here is a steady flow system. Anyway, measuring. So measuring 20 degrees Celsius, what was measured? It's the entering state, which is, in this case, I will then name it as state 1, right? Temperature entering is 20 degrees Celsius. And then, now you might think already, I want to improve, or I want to improve the speed at which I saw, right? So, think about this. Your substance is air. What else are you going to do? Air is an example of an ideal gas, so at the very least, maybe you might want to make things a little bit easier for yourself, what we call mise en place, right? Mise en place, yes, just skip a little, skip a minute or two if you already know what this is, but in French restaurants, or basically just in restaurants, right? Chefs need to prepare a lot of different dishes, which require a lot of different ingredients for a lot of different people at a lot of different times, right? The thing is, if you're not organized, chaos will ensue in the restaurant, in your workplace, in your scratch paper, unless you already try and expect things to happen, right? So what they do, what mise en place means to them is that they chop the vegetables already. So they have pre-chopped onions or whatever, right? And they know where to put the stuff. All of the vegetables are here, all of the fish is here, so on and so forth. They have different systems, right? They have different chopping boards, they have different knives so that you don't cross-contaminate in case someone is allergic, something like that, right? In this case, what I like to say when I like to say mise en place, what I mean to say is that I want to make it easier for myself to already try to solve. Like, say for example, when I see this, I see, wait a second, I'm dealing with air. And I already know that air should be handled as if everything were absolute. This is not absolute. So if you want, you can add 273.15 to this already. You can already replace this with 293.15 Kelvin. If you want, of course, right? The thing about this is that now when you're in a bit of a rush, you see this, you will thank yourself because at the very least, okay, buti na lang, right? It's good that my past self thought of already computing this so that I don't have to in a time crunch, right? So that is what mise en place means. Same way with 1 bar in here. 1 bar is not very computable for air, which is an ideal gas. So let's turn it into kPa, right? That's what we need in the first place, 100 kPa. And a volumetric flow rate of 0.25 cubic meters per second. So V/1 is 0.25 cubic meters per second. It then exits at 50 degrees Celsius again, right? T2 is 50 degrees. You can choose to put it like this, or you can just add it to 273.15. You will get 323.15. Let me see. Yeah, I did add that correctly. And then 0.95 bar. So again, we turn this into kPa, 95 kilopascals. And then through a flow area of 0.04 meters squared. Thing about this is that because technically that is only A2, the fact that we were already thinking about constant diameter, meaning constant area, that's another kind of mise en place. Now you already are kind of helping yourself out in the future. And hey, this is a good note, 0.04 meter squared. Assume K is equal to 1.4. Technically, I don't even need to take note of this, but there you go. Your K is 1.4. Okay. Now, what we need is, number 1, the mass flow rate. Okay. Number 1, the mass flow rate, m dot. The velocities at the inlet and the exit, so vel1 and vel2. Okay. And then the heat transfer in kilowatts. Okay. So I have a little note down at the down when we're going to solve for our heat transfer, or actually our velocities already. But the thing about it is this. What I said before. This is fun because technically you already know what you're supposed to do. The solution is always write down the first law. Q minus W equals delta KE plus delta PE plus delta H. This will get boring. Okay? I understand that will get boring, but the thing is, you start here. There is no other starting place but here. Right? And so now, we start canceling. This is the fun part. Right? The fun part is, well, there is no mention of this pipe moving at all. Therefore, there is no work. Okay? This pipe is being heated. So, well, there is no other choice but to assume that there is heat. Right? And of course, you're going to solve for it later, the heat transfer. So, we will let this remain for now. We do not know the velocities of this thing. So, that means we don't know if we should actually cancel our KE or let it stay. Because, for all we care, maybe the vel1 and the vel2 are the same. Maybe, at the very end, there is no change in kinetic energy. But for now, we can't tell yet. Now, for delta PE, there is no indication of elevation, which makes it seem like, well, we don't know yet, but actually we do. we can cancel this because of the little word in here, horizontal. Horizontal means that there is no change in elevation because, well, the level of state 1 is just the same as state 2, and this leaves us with delta H. That is very clear to me that there is a delta H in here because look at this. The temperature rose. Of course, right? Delta H, or rather enthalpy, is just internal energy and then flow energy. Thing about this is that it's very clear that the internal energy has increased. Now, it is up to everybody, right? It is up to you to determine what to do next. And I suppose this is the hard part, right? But the thing about this is that technically, I've stopped giving you new information, right? Now, we are going to recycle everything that we know, right? All of topics 1, 2, 3, and 4 are going to come back in here, and this will be our base. This is our knowledge base, right? All right, let's begin creating a plan. Well, it's not just the Q that we're going to find, it's all of these other things as well. And if you guys have been listening, right, to my discussions for quiz 2, usually Q is computed last. Because, well, for you to compute Q, there is no formula. You will only compute Q once you have known every other term in here. You don't know delta KE, you don't know delta H, so you cannot compute for Q yet. All right, so that remains a mystery. That remains the final thing to be solved. Well, what about something that is supposed to be easier, like m dot? Where will we get m dot? Well, because of the mention of m dot, there's another kind of equation that will help us. Not only is the first law the thing that we need, because we are operating under steady state or steady flow, we can now use the continuity equation. Rho 1, A1, vel 1, right, is equal to rho 2, A2, vel 2, right? All of that, let's remember, is just equal to m dot, right? This is the thing that we need to find. Do we have a rho 1? No. Do we have an A1? Yeah, we do. Right? Do you have a vel 1? No. Do you have a vel 2? No. We actually need that. Right? Do we have an A2? Yeah. Do we have a rho 1 and a rho 2? I don't think so. But the thing about this is, because this is an ideal gas, you already can get something from your knowledge base. There is a formula for the density, which is going to be density is equal to P over RT, or our pirata, right? That is our mnemonic. Right? P over RT, pirata, pirate. And so in this case, we can actually get the rho 1 and rho 2 because of the fact that we now have a P1, T1, and a P2, and then a T2. So let's just get it. Right? Let's just get what is supposed to happen in here. Well, we can get rho 1, right? We can get rho 1, which is P1 over RT1. And then we can get rho 2, which is P2 over RT2. But the thing is this. I will tell you right now, this is completely fine, right? As a solving mechanism, this is completely fine. However, at this point, you might already get the itch to be like, I want to get to the answer now. You know, sometimes, right, we are now under a painful realization that, wait a second, what I'm doing is correct, but it's too slow. Or you feel that it's too slow. Maybe it's the correct, maybe it's the correct rate at which you're supposed to do things. Maybe you're supposed to do things a little bit more slowly. I remember one time my professor in calculus handed me a paper from my quiz. And what happened at that time was that because it was a 7:30 a.m. class, I was 15 minutes late. And then because, I was young back then, I didn't know a lot. I just knew that I was good at calculus, and so I kind of wanted to show off, which was a bad idea, of course. I submitted the paper 15 minutes early. So instead of taking up the whole 1 hour 30, right? I only was afforded 1 hour 15. It was actually good that he just gave me the opportunity to still take the exam, right? So I had 75 minutes. I didn't use the 15 minutes. I just took the whole hour. And then it's just, a little sign saying that, you know what, I don't need to check. And he laughed at my face. He was like, "You thought you were gonna get a perfect score? No, right?" And there was a massive note in there that, like, if you just went to this class a little bit early for the 15 minutes, and if you took the time to check your answer and see that it's wrong in the last 15 minutes, you would have gotten this, right? And so that was like a big humbling moment for me. And I'm like, oh, okay, maybe I should slow down, right? But sometimes, we get the itch na, like, maybe what I'm doing is too slow, right? So there is, right, of course, a way forward, which is just, it's not being asked, right? Row 1 and row 2 are not being asked. The only thing that is being asked in here is, well, is your M dot. So who needs this, right? Technically, if I see this in your solution, I'm going to just nod my head and say, okay, that's what you did, right? But there are no brownie points in here, right? If you write everything in your solution, it's going to be fine, right? At the expense of your time. What I'm suggesting in here is that if you find that this is too slow, I suggest you go directly to the source. What do you mean directly to the source? Well, just put this in place of this, right? Instead of writing down m dot is equal to row 1 a1 vel 1, why not write down m dot is equal to row 1 over r1 over p1 over rt1 times a1 vel 1. Why not write that down? Right? Of course, you're going to see in here that you can get the value of P1, T1. R of air should be memorized. A1, but there's still no V1, vel 1, right? So how are we going to compute for M dot? The same thing will exist for state 2. I don't know that. But, right? When you are so deep in the trees, you don't know the forest. I forgot how that quote goes. You still have V slash. V slash is, right, is the same thing as area times velocity, right? Hold on. Let me get that actually. All right, I'm back. That was my nighttime alarm. Okay, a little clue as to when I am recording this. But anyway, V slash is also equal to A vel. So V slash 1 is just equal to A1 vel 1. You don't need to know what vel 1 is for you to solve this thing, right? You can just, again, put this as V slash 1. Now you have everything on the right-hand side. You can solve for your M dot. And another way, right, another very valid way to get to this is, if you remember, PV is equal to MRT. Because we're dealing with an ideal gas, it does not matter if you are dealing with a closed system, in other words, only using M and V, or if you are using an open system or a steady flow system. Now, instead of V, you'll now use V slash, and instead of M, you will use M dot. Notice that if I just move the R and the T down, you will still get the same thing. So they're all connected, right? Even if, right, say for example, someone might get their answer from the continuity equation. Okay, that's good. Someone else might get their answer from just saying, you know what, if PV equals MRT, then PV slash is equal to M dot RT. That's also completely fine. And so now we can just solve for this. We will get 100 kPa times 0.25 meter cube per second all over. We have our R here, which is 0.2871. Hopefully, you guys are starting to put all of that together. kJ per kilogram Kelvin, and this is now 293.15 Kelvin from before. Let me see if I got this correctly. PVRT. Okay, everything is good. Let's look at the units before we say anything else. Your M in here will have units of kPa times meter cube per second. Actually, let's bring this a little bit away. So maybe here. kPa times, or you know what, just down here. This is good. kPa times meter cube per second all over kilojoule per kilogram Kelvin times Kelvin. You can cancel. And what you can do is you can turn kPa into its Newton and square meter, kilonewton per square meter. Notice that there are 2 copies of meters in here and 3 in here, so you can cancel. You will be left with an M in here, and notice what a kilonewton meter is. That is the same thing as a kilojoule. And there's a kilojoule on top, and there's a kilojoule at the bottom. Cancel. And notice that there is a per kilogram in the denominator. So what you can do is you can flip that, and everything will come down to kilogram per, there's a per second in here, kilogram per second, which is indeed your m dot. So that means you don't have to do this anymore, right? Cool. So if you put all of this into your calculator, you should get something like, I already have something in mind, I think, yeah. So it's 0.2970. Everything in here I will do 4 decimal places just for safety, right? So that is your m dot. Congratulations. Next, we will go to our vel1 and vel2. Now, if we think about it, wait a second. We kind of already know, or we're already supposed to know what vel1 is because of this. You now have a v/1 and you have an a1 because it's a constant diameter pipe. So now you should be able to get your vel1. So let's get vel1 as well, right? So we know that v/1 is equal to a1 times vel1. So we can just say 0.25 meter cubed per second is equal to 0.04. This is meters squared. And then our velocity in here, I will assume, right, that this is in meter per second. And in fact, it does span out. Right? Look, there are 3 copies of m in here. There are 3 as well in here. So cancel everything. And then there's a per second in here as well. So you can get your vel1 in here. And that is, I remember this. This is 6.25, right? 6.25 meters per second. That is your vel1. Okay. Now we have vel1 as well. We will get vel2 next. How will we get vel2? Well, we can still make use of this continuity equation. The thing with this is now we have updated a few things, right? This is now, right? This is now possible. We can now get this. We can now compute for this. We now have vel1. We can now compute for rho 2. And in fact, we have now a kind of a condensed formula, which is this. Right? So we can just get m dot, which is now equal to rho 2 v/2, or in this case, a2 vel2, right? a2 vel2 all over r times t2. In this case, your vel2 is now the thing that we can find. And technically, what you can do is you can shift solve. What I will do is the old-fashioned way because, you know, I'm very antiquated like that. Right? I will now raise the RT2 and then I will lower the pressure times area right here. What we will get is basically vel2. You know what? Yeah, here works. Vel2 is equal to m dot times RT2 all over P2 A2. Okay. Let's try this out. What we will have is basically m dot 0.2, what was that again? 2970 kilograms per second all over times 0.2871, right? Kilojoules per kilogram Kelvin times your T2. Your T2 is now going to be your 323.15 Kelvin all over your P2, which is now 95 kPa. This is now the second, right? And then this is now the second pressure, right? The pressure exiting. And your A2 is 0.04 square meters. Now look at everything, right? Let's look at the units, even though technically we don't have to. We already have tried this before. It should become vel2, but you know, it's quite fun. Cancel. You will have on top a kilojoule per second. Technically, that's a kilowatt already, but I digress, right? There is in here a kilopascal times a meter squared. We know that a kilopascal is just a kilonewton per square meter times a square meter. Cancel, cancel. You will now have this thing. And what you will see in here is that a kilojoule is just the same thing as a kilonewton meter, right? Kilonewton meter per second all over kilonewton. Cancel, cancel. You will indeed get a velocity, right? You will indeed get a velocity. So our vel2 in here will become, let me just see this. This will become, you will get 7.2522. 7.2522 meter per second. This is our vel2. Again, I'm using 4 decimal places just for accuracy. Okay? And then, finally, we now have enough, or maybe we now have enough information to tackle Q. So let's go back and let's try and update our values in here. We now know vel2. We just computed for vel2. If we know vel1 and vel2, we should now be able to detect our change in kinetic energy. Right? Right? So that is now something maybe that we can find. What about enthalpy? Right? We still don't know enthalpy, but now, right, if you have yet to understand where we're supposed to get this, you are working with air. And with air, it's an ideal gas, and a lot of things are simplified with an ideal gas. Usually, your delta H is just going to be equal to m times H2 minus H1. But the thing about this is that, well, you don't have values of H2 and H1. It's because, well, you don't have a table, a property table for air, right? What you do have, however, is the CP, the specific heat. A CP, right, is your change in enthalpy per change in temperature. The same way that your CV is a change in, right, your change in, what do you call this? Internal energy per change in temperature. What you can do is you can manipulate this. You can multiply dt to both sides, and you'll see that your dH is equal to Cp dt. Oh, that means that your delta H, when you're talking about ideal gases, is just MCAT. MCP delta T or MCP T2 minus T1. So let's see if we can get our delta H. Yes, we do have an M dot. We do have T2. We do have T1. But we do not necessarily have a value of Cp. So, where are we going to get the value of Cp? There are 3 schools of thought. Number 1, if you are a by-the-book person, go ahead, consult the book. Here are our tables. And the thing to consult when we are looking at ideal gases is, of course, what is happening? Oh my gosh. Acrobat Reader is not very good. They might. Please don't crash. This is a PDF. Why is this so bad? All right, fine. Okay, let's just pull this up. I think okay. There you go. I just want I just want there to be like a dedicated kind of did it hang again? Okay, there it is. I just want there to be a dedicated kind of window for the tables, but apparently they're not oh my gosh. What do they think about this? Is this resource intensive? This is just reading a P anyway. We're here, table 820, right? This is the table that you need if you're dealing with ideal gases, right? If you're a by the book person, right, what you will think is that, okay, there are two different temperatures, right? 293 and 323. What I've told you guys to do back in topic 4 was that for you to get, right, the Cp, Cv, and K, right? Notice there's a Cp, Cv, and K for air at different temperatures. What you're supposed to do is you're supposed to average the temperatures right here. So the average of 293 and 323.15 is, what was that? This was 20 and then 50, right? 20 and then 50, so the average is 35. So the average in here is 308.15. 308.15, I'll pull out an engineering move, is close enough to 300. So just use CP is 1.005. Technically, if you want to interpolate this, go ahead, right? That will waste your time, right? Well, you have to pick your own battles, right? So in this case, from table A20, right? What you might say is that number 1, right? From table A20, you might get an answer, which is your CP of air is 1.005 kilojoule per kilogram Kelvin. You might say to yourself, or someone else might say, you know what, why should I even get from the table? I have memorized something. The something is that there is actually a formula for CP. If you know the value of the adiabatic index K and letter R, right? The R of air, the specific gas constant of air. The formula is Karki, KR over K minus 1. And if you want, go ahead and compute. 1.4 times 0.2871. Notice in here that only R has a unit, right? K does not have a unit. It's just an adiabatic index. So this is just 1.4 times so on and so forth. We will have an answer of 0.4. You will have an answer of 1.00485. Wow. Right? And I say wow sarcastically because notice that there is not much of a difference from, right, your 1.005 and your 1.00485. The third person might say, you know what, you guys are all stupid. You can just memorize the value of CP of air. The value of CP of air that I will accept is 1.005. Okay? Sometime down the line, you might see a kind of solution wherein they might say 1.006. That's fine as well, right? When you're trying to be conservative, maybe 1.006 may work, right? And some people who just don't give a damn, they just do one, right? Which is somewhat a little bit preposterous now, but honestly, right? It's not a big difference, but still, I would like to standardize. If you would like to memorize, right? If you like to memorize the CP of air, it is 1.005 or 6, depends, right? And that means that, well, by consensus, I'll just use 1.005. It's close enough, right? And so that means we now have a value for CP. Congratulations to us. We can now solve for delta H. And now technically we can solve for Q, hopefully. And now this is where we are going to run into a problem. Let's just try and solve for Q. Q is now delta KE plus delta H. And then this is where you're going to start encountering the issue. This is going to be KE finals, or KE of state 2 minus KE of state 1. This will be 1/2 times M vel 2 squared minus 1/2 M vel 1 squared. Do you notice the thing that I have deliberately not written down? Usually, when I speak, say for example, when I speak about delta H, right? Earlier I just said M times H2 minus H1. I did not bother to say M dot, but I still put the dot on top. And so this reveals a kind of a technicality, right? When you are working with the first law for open systems, it is technically just a little bit more different than just using delta H instead of delta U. This is valid for closed systems, right? We know that this is valid for closed systems. For open systems that are steady flow, the actual valid equation is not this. But it's also not this. The technical valid formula should be ... Everything in here is not a change in kinetic energy. It's not a change in potential energy. It's not a change in enthalpy. It's not a change, or it's not a heat transfer or a work transfer. Everything is a rate. Why is that? Because, well, you don't have a mass. you instead have a mass flow rate. And so what I'm doing now in here is that I'm dotting everything because technically we are under an open system. We are under an open system. Everything is in steady flow. Some stuff is going in, some stuff is going out, and everything is measured in a rate of heat transfer, a rate of change of enthalpy, a rate of change of kinetic energy. But notice that I don't, right? I don't care, right? I treat them as interchangeable because, well, in an open system, where else will you find a mass? Right? Where else will you find a mass? You cannot find a mass except if it is as a flow rate. So, if you want to be very pedantic, you want to be very technical, in an open system, everything has to have a dot on top. Because, well, you are using mass flow rates instead of masses. This is actually a telltale sign that you're working with a closed system or an open system. If you're not sure, right, what is happening, you can ask what the mass is. If the problem replies with, oh, kilogram. Oh, okay, so I'm working with a closed system. But if they reply with a kilogram per second, you now know, things are flowing. That's an open system, right? So that's actually a good sign. And so that means actually that your Q is no longer in kilojoule. It's no longer in kilojoule. And if we look back, it's actually in kilowatt because you are now looking at a rate of change. So it's kilojoules per second, which is now kilowatts. Okay. So that's just something that I want to share. Okay. Now, we will talk about this is now your rate of change of kinetic energy. This is not a change of kinetic energy, but the rate of change of the kinetic energy. And now this next one will be m dot times Cp T2 minus T1. Let's just tally everything, see if we have everything in here. We always have our M's, our vel2 and our vel1 are all good. You can see that everything is here. We can now solve for our Q. But then, right, you can see in here, 1/2 m dot, 1/2 m dot, you can actually just group them together so that it's easier when you're going to compute. Your m is going to be 0.2970 kilograms per second. And then this is going to be vel2 squared. This is 7.2522 squared minus 6.2500 squared. This is now meter per second, but then you square it, so it's meter squared per second squared. And then plus our m dot 0.2970 kilograms per second times your Cp, which is, we just said this was 1.005 kilojoule per kilogram Kelvin. And then now with your T2 minus T1, technically you don't even have to put down 323 and 293.15. You can actually just use your normal temperatures, 20 and 50, because we are looking for temperature difference, not a temperature reading. When a temperature difference is required, actually, degrees Celsius and Kelvin are interchangeable. Degrees Fahrenheit and degrees Rankine are also interchangeable because if you think about it, right? Say, for example, if I just write down here 50 and 20, and someone's going to tell me, hey, you should add a 273.15 because, well, it's an ideal gas. So you do so, plus 273.15, then plus 273.15. The thing is, because this is negative, you're going to cancel them out anyway. So it's wasted effort, is what I say, right? So you don't need that, right? 50 minus 20 is good enough. And if you can do the math in your head, then good, right? Just write down 30. I don't care, right? I will get why you wrote down 30 instead of just like 50 minus 20. Okay? And now here's the thing. It's very it's very tempting to just put all of this in your calculator. I will do so right now actually. 0.5a times 7.2. I will do this, and as I am putting this in my calculator, hopefully you guys are already spotting what is wrong with this thing, right? What is wrong with this thing is that you will get an answer which is 10.9656. Oops, 9.9656. The thing is though, right? Because it's in kilowatts, you're saying, it's in kilowatts. You're saying, okay, this is the answer. But actually, this is wrong. Why is this wrong? Because you did not look at the units. Back in topic 3, right? I issued a warning to everybody, right? I issued a warning that, well, if you're going to combine kinetic energy, potential energy, and internal energy, you have to be very careful because usually values of H or U are much, much larger than the values of KE and PE. Look at this. This is basically our delta KE, and this is basically our delta H. Notice the units for each term. For delta KE, let's look at the units, right? For delta KE, the units are kilograms per second, right? And then this is now meters squared per second squared. Meters squared per second squared. Now what I can do is that I can break the two M's. There you go. Because I want this. Kilogram meter per second squared is basically mass times acceleration. Newton says that that is just your force or your Newton. And then next, Newton times meter, that is just the same thing as a joule. And that is a joule per second, which means that all of this is in watts. Oh, so immediately that is already a wrong thing because we forgot that everything should be in kilowatts. So there should be a 1000 division in here. We already know that everything in here is in watts. So let's just have a 1000 watts in here and then 1 kilowatt to solve the whole problem. Notice that for the delta H, we will just have kilograms per second times kilojoule per kilogram Kelvin times Kelvin. Cancel, 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 cancel. You will have a kilojoules per second, which is very clearly kilowatt. So there is a mismatch. You needed to divide by 1000 for the KE. And for the PE, you will have to do that as well. But for the delta H or for the delta U, you don't have to. That is the scale at which the you will find these two, right? So what textbooks will usually do is instead of saying that this is 1/2 m dot vel squared, they will immediately say 1/2000, just to train the students who are reading the textbook that, hey, this will give you units of kilowatt. Okay, but let's do it ourselves. Let's just have in here a little 1000, right? And then maybe the next time that we're going to use it is just 2000, so that we already know, I see. So this is going to be in kilowatts immediately or directly, right? And we will now have here the correct answer, right? The correct answer, which is not this, but, right, your Q dot, right? And honestly, guys, you don't have to worry about the dots, right? I will understand that this is heat rate, right? Heat transfer rate because it's in kilowatts, okay? It's in kilowatts. The correct answer is 8.9578 or 8.96 kilowatts, okay? So if you're solving along, good job. There you go. That is our answer. So notice that is a humongous solution, right? The thing is, right, in the board exam, again, I'm going to rave about the board exam. You don't need a solution, right? If they find your answers suspicious, well, they'll call you out because, like, I don't know, if you don't literally have nothing on your paper, maybe that's suspicious. But like, you don't have to explain to the PRC that, oh, hey, this is what I did, right? Sometimes, a guess is enough for them. Maybe they said, you know what, we'll let this kid pass, right? This person, he guessed enough times, he got a 70. Let's give him the license. Okay, right? What I'm saying in here is that if you are at a crunch for time and if you already know what to do, maybe you can choose to forego some of this thing. Maybe you don't have to put this. Maybe just put this and then boom, I will understand, right? So long as, of course, you get You can point to values of m dot. You know, or rather, I should know what the R of air is. You have the T2 here already. Your P2 is here, and then your A is somewhere in here as well. I will understand if you just write down this and then this. Right? Of course, I will also understand if you have everything in here because you want a logical kind of way forward. Okay? But that is problem 1. Right? Again, if you guys have any questions, let me know. Okay? That is problem 1. Right? So there you go. Those are our answers. Right? And now we go to the cousins, I guess, closely related, the members of the pipe family, which is the nozzle and then the diffuser. These are just pipes wherein their cross-sectional areas change. For the nozzle, it gets smaller as it flows through, as the fluid flows, right? And for the diffuser, right, it gets larger as the fluid flows. Both of these things are ideally isentropic. Isentropic in the sense that the fluid will flow through this boom so quickly that there is no heat that will be transferred into or out of the pipe, right? And so if we're saying isentropic, if we're going to see this, of course, these are just pipes. They will not move. And because this is isentropic, you should also have no heat transfer, right? The thing about this is that nozzles and diffusers are usually, not all the time, but usually horizontal, which means, there you go, delta PE is 0 as well, which means that there is now a relationship between the kinetic energy and the enthalpy, right? You will now see in here that they are equal to 0, right? If we're going to write this down, delta KE, right, plus delta H is equal to 0. So that means, right, that when one goes up, the other must come down. We will look at a nozzle right here. And this nozzle will have 2 different states. One going in, the big area, and the one going out, the small area. And this is the first state, right? It has a kinetic energy. It's represented by the thickness of the arrow. And it has a potential energy. It's represented by, again, the thickness of the arrow and enthalpy. This is just to represent that enthalpy here is quite large compared to kinetic and potential energy. And now notice, the change in PE is 0, which means the potential energy is the same, right? But now, because what happens in here is that the what do you call this? The area gets smaller. Of course, it makes sense that the fluid inside will travel faster, right? And that means the kinetic energy rises. Okay, if the kinetic energy rises, right? Well, then something else has to fall. Oh, the only thing that can fall based on this first law is the enthalpy, which means, boom, they will now switch places, right? Well, okay, to be technical, they won't switch places. It's just that the kinetic energy will rise at the expense of enthalpy. Of course, enthalpy will still be quite large, but in this case now, your kinetic energy has risen, your enthalpy has decreased, right? And now that is the gist of it, right? And you might be wondering, what? Because the enthalpy went down, what? What do you call this? The fluid became colder? Well, not necessarily, right? If we're talking about Bernoulli's principle again, another way that you can lose enthalpy, that enthalpy can decrease, is that if your pressure decreases. And that is how it works, right? If the speed of the fluid increases, the pressure that it bears, or rather the fluid pressure that it exerts also decreases. It's a very interesting consequence. For diffuser, you literally just turn this around like this, right? So for a diffuser, what happens is that the kinetic energy will decrease because, well, your fluid will slow down. It will encounter a larger area, and that is it, right? Your kinetic energy will decrease and your enthalpy will increase, meaning that the speed will decrease, but the pressure will increase, right? And so we will go to another problem, 5.2, right? We will apply those things that we've learned. And now steam interacts with a high temperature horizontal nozzle operating at steady state. Entering a 30 bar, 440 degrees Celsius with a velocity of 20 meters per second, and leaving at 10 bar at 240 degrees Celsius, the steam is known to have a mass flow rate of 0.75 kilograms per second. That's a lot. Supposing that the operation is adiabatic or an isentropic, relatively, kind of maybe, right? How fast is the steam going at the exit in meters per second? And how big are the inlet and the outlet in square centimeters? Okay, so we have here the copy in 5.2. There you go. Right? And now we can draw again. We have a nozzle right here. So of course the what do you call this? The pipe will get smaller. So let me draw in here. And then we will have this thing. Because we're very fancy. There you go. It's getting smaller. It got really small. And then now this is our pipe. Right? This is now our pipe. So we will have your state 1 right here. And then your state 2 right here. Actually, let's just draw them outside. 1 and then 2. Thing about this is that, of course, you're going to see in here that the nozzle will have a bigger A1, right? And a smaller A2. This is already an explicit assumption, right? The thing about this is that I'm saying this out loud because I don't know, maybe it's not as obvious to you guys at the outset, right? But I'm just saying this because you should rely on your reality checks, your gut checks, your sanity checks, right? Maybe your answer does not make sense, but you just put it as the answer because, well, it's what the calculator says, right? It can't be wrong. Of course it can be, right? Now, we are working here with steam. Congratulations, we are no longer working with an ideal gas, which means you will go back to your tables. Maybe if that's easier for you. For me, it's not, right? Go ahead, right? A high temperature horizontal nozzle. Horizontal meaning, again, there's no change in potential energy. So honestly, you can already start, right? You can already start with the solution, right? The solution is as follows. Again, you will write down the first law. Q minus W, KE, PE, and then delta H. And then, right, horizontal, poof, cancel, right? Entering a 30 bar, right, 440 degrees Celsius. What I will do now in here is that I will just put in here, state 1 is 30 bar, for 30 bar, 440 degrees Celsius. You might say to yourself, well, why aren't you doing the same kind of detail as in here? Well, it's because it's obvious to me that because it's steam, right? Because the substance is water, they are going to make me look at the tables. In the tables, the units for pressure and temperature are in bar and in degrees Celsius. So, this is the only thing I should be looking out for. If anything, say for example, if it were expressed in kPa, I would turn it into bar because, well, the bar is what you need for the table, right? Entering a 30 bar, 440 degrees Celsius with a velocity of 20 meters per second. Vel 1 is 20 meters per second. And leaving at 10 bar, 240. 10 bar, right? 240 degrees Celsius. The steam is known to have a mass flow rate of 0.75 kilograms per second. So that's actually a lot of steam, right? So I paused here a little bit earlier because I was thinking, how big is that steam? Right? You might say to yourself, okay, 0.75 kilograms per second is already a fast hose. Imagine 0.75 kilograms or 750 mLs of water. That's per second coming at your face. Right? So that's water. Okay, sure. So you might say, okay, that's already quite a lot of water per second. Now imagine it as steam. Hot, hot, hot steam. That's a lot of steam, right? Especially because steam is now a vapor. How can vapor weigh a lot? And now you're telling me there's a lot. So I'm already setting myself up for expectations here that like, ooh, this is going to be out of my intuition, right? I'm telling you guys a lot to rely on your intuition. And now this is the time to say that, well, this might be a little bit out of my intuition because this is a lot. There's a lot. Okay? Anyway, right? The steam is known to have a mass flow rate of 0.75 kilograms. Supposing that the operation is adiabatic, that's our key. Cancel the Q. And because this is a nozzle, well, it's not supposed to move, right? you also cancel the what do you call this, the work. Right now you will have delta ke plus delta h is equal to 0. And notice I will now expand them even before giving off, right, or even before listing down what is required. This is the given, of course, right? I will expand, right? What I will do is 1/2 m, or rather instead of 1/2, because we already know that we need everything to be the same unit, instead of 1/2 I will now say 1/2000, right, times m dot, and then you will know that this is vel2 squared minus vel1 squared plus your m dot times h2 minus h1 is equal to 0. Notice I'm using this now because, well, technically this is the general sorry, Cole. Sorry. Cole is under the table. This is the general form, yes, but also, well, you cannot turn water into an ideal gas. Okay? So Cole is now licking my feet. Anyway, she's lying down on my feet. That's sweet. Anyway, the thing is now, this is a glaring clue for us to say, okay, I should get H1 and H2 from the table, right? All right, so we should probably have a little to-do list in here. To do, I will get H1 and then H2, right? H1 and then H2. I will not look at a table yet because maybe later down the line we need something else, right? But notice, I can actually cancel my m dot. Because, well, if you cancel, or if you divide both sides by m dot, which is just a number, right, you will still see this. See, everything is still possible. So you will now have vel2 squared minus vel1 squared all over 2000 plus h2 minus h1 is 0. Congratulations, you have unlocked a new formula, right, by watching this video. This is the formula that is valid for both what do you call this? That is valid for both a nozzle and a diffuser, supposing that it's number 1 horizontal, number 2 adiabatic, right? Which is usually what is being assumed, right? Now, let's tally in here. I can probably find the value of H2 and H1. We can find, or rather, we are being given vel1. Therefore, we can find the value of vel2 immediately. Right? This is what mise en place allows us to do. When you're just reading the problem and you're reading it slowly, what you can do is already record the stuff that you know, and before you know it, I haven't even read this again, right? But now we can say, I can definitely solve for vel2. Now, Nicole can solve for it too. Say hello. Okay. Anyway, we can now solve for vel2, right? How fast is the steam going at the exit? Required is vel2, which is now something that we can solve for. And then, how big are the inlet and the outlet? So A1 and then A2. Okay. So now, let's try and solve for vel2. Before that, we need to get values of H2 and H1, but I'm pretty lazy. I don't want to alt-tab. Maybe I can get everything already in one go. Okay, by everything in one go, maybe I need something else from the tables. So I just want to go to the tables once, right? So maybe this is just a little quirk that I have. Maybe you guys don't feel the same way. But let me look at trying to solve for A1 and A2. Maybe there's something else in there that we need. Okay? Maybe there's something else in there that we need. And where else would A1 and A2 be necessary? Where else would they be required except in the momentum tuloy. Sorry, that's a Freudian slip. That's in your mech flu subject. It's in your continuity equation. In my defense, there's also a continuity equation in mech flu, right? So your m dot is equal to your rho 1 a1 vel 1, right? And then that is also equal to your rho 2 a2 vel 2. Looky, we need, right, a1 and a2. We already have vel 1, and we just said earlier that we can very well, right, compute for vel 2. We have a value of m dot, so that means that if you can use, right, if you can find somewhat or somehow a value for row 1 and row 2, you can get your values of A1 and A2. However, you can't. This is not an ideal gas wherein you can just divide, you can replace this with P over RT. Right? I understand there's a pressure and a temperature. It's very tempting, but please do not think about water as an ideal gas. Okay? Cole agrees. She's rubbing her face on the microphone. The thing about this, though, is that we should not lose hope because there is another way that you can represent rho. Its reciprocal is specific volume, which is V1. Its reciprocal is V2. This is what I mean when I say maybe you're gonna have multiple trips to the steam tables. If we didn't catch this immediately, I would have had 2 trips to the steam tables. I don't feel good when I'm in that zone because I'm at the risk of interpolating. And because I made these questions, I'm not going to make myself interpolate. However, for you guys, it's a different story, right? V1 and V2 can be very well can be just gotten from the tables. So we should add that to our to-do list. Okay? So V1 and then V2. Note that I'm very confident because we are being given 2 values or 2 properties each state, a pressure and a temperature, and if this is not yet very obvious, right? It's steam. It's a superheated vapor, right? So both of these things are superheated vapor. So let's just look at our superheated vapor tables. Table A4. I'll now use the scroll because apparently they don't want to scroll properly. We will go to, what is this? First 30 bar. Hopefully there is a 30 bar. And who are we kidding? Of course, I'm not going to give myself interpolation. 30 bar, 440 degrees Celsius is this row, right? So that you don't have to look up, right? So you can see I'm very ergonomic like that. Let's just remember that this is in the form of V, U, H, and S. That means that your first number will be V, the second is U, third is H, and then last is S. So just get the values of V1 and then H1, which is in this case 0.1062. Oops. 1062 meter cube per kilogram. This is from our A4. Right? Honestly, everything is here. Everything is from A4. So I'll just write in here A4, 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 and then A4. And then your H1 is going to be 3321.5. 3321.5 kilojoules per kilogram. Now, for your state 2, it's 10 bar to 40 degrees Celsius. Right? As much as I'd like to keep the charade up, again, 10 bar to 40, I don't want to interpolate. So there you go. That is your V2 and your H2, which is now 0.2275. 0.2275 meter cube per kilogram. And then your H2, which is 2920.4. Now, I understand if you guys don't agree or identify with this kind of problem-solving technique. It's just for me, I find that I'm like this for like a lot of my life. When I eat my food, right? Say for example, when there's ulam and then there's rice, I usually eat all of the rice first. I don't eat a lot of the ulam, the meat, right? And as a result, right, at the end of my rice, right, there's a lot of meat. So that is a reward to myself. Now, yes, finally I can eat all the good stuff at the end. Notice that what I'm doing here is I'm setting up everything so that I can just get through everything in one fell swoop. That is my personal style. Okay? I understand if you guys do not identify with that. It's just that I'm already giving you the path ahead. I'm planning ahead so that, well, at the very least, an advantage of this is that you are already seeing ahead. Right? You're already seeing ahead in terms of, well, if I can solve for Vel2, then what? Right? Because now we were able to look ahead na, okay, because we solve for val2, now what, right? Now we are able to find that, oh, I actually do need to find values of v1 and v2. Over time, of course, you will develop an intuition na like, I think I need to find v1 and v2. Sometimes you might say to yourself, because I have done this a couple of times, I told myself, you know what, I'm just gonna get v1 and v2, or I'm just going to get the v of this state just in case. And in fact, it did come true, right? So you will be developing that intuition, of course, so long as you continue solving. Okay, now enough talk. We can get to val2 immediately. Okay, the thing about this is, again, I'm quite old school. I will solve for this the old school way, which is you put this to this side and then multiply both sides by 2000. You'll get something like this. val2 squared minus val1 squared is equal to 2000 times, because I'm now flipping them, right? I'm now putting them to the other side. They will get negatives. So instead of h2 minus h1, I will go h1 minus h2, right? And then I'll put this here, and then because this is squared, I will square root, right? And this is very important because, well, this, if you want to memorize this, go ahead, right? val1 squared plus 2000 times h1 minus h2, right? This is already a good parang formula, if you want, of course, again, to memorize what we're supposed to do. 20 squared plus 2000 times your h1 is, what was your h1? Our h1 is 3321.5 minus your h2, which is 2920.4. 2920.4. Notice that I am not bothering with the units. I'm not bothering with the units because we have already taken care of the units, quote unquote. We've already taken care of it because we are ensuring that with this 2000, instead of just the 2, that everything in here is kilowatts. And that means that we don't have to worry about the units. Our units in here are going to be the default ones that we have been working with. Okay? So if you're worried, hala, this is in kilojoules per kilogram. Oh, hala, this is in meters squared per second squared. Are they the same? It doesn't matter. Really, it does not matter. Right? Because we already took care of the units from earlier. If you want, you can go through all of the units and you will find that because of the extra 1000 in here, everything is accounted for. Right? You can do that by yourself, but in here, we already know that the units should be in meters per second. So I'll put this into the calculator. We will get 3321.5, 2920.4. We will get 895.8795. 895.8795 meters per second. So this is your val2. Before we box, or after I'll box, I will ask you guys a question. Do you guys see something wrong with this answer? Because I do. There's a gaping hole with this answer. And the hole is that this does not make sense. What is this? What is this answer? You might be wondering, like, what does he mean? Well, the thing is, the speed of sound is 343 meters per second. You're telling me this is breaking the sound barrier? Well, I did say before that this is an absurd amount of mass flow rate. But that's different. But the thing in here is that the sanity checks, right? They come at a cost. They come at a cost of you being very critical of everything. Especially when something like this is going to come out. Maybe you didn't even think about this. All right, okay, you don't have to doubt this answer because technically we did nothing. We didn't do anything wrong, but it's just now that you think about it, this steam is way too fast, right? But the thing is, well, where is that change in enthalpy going to go, right? It's going to go and make your velocity faster. Mind you, this is the correct answer. Okay, and now because we have the correct answer, we can now solve for our values of A1 and A2. What I will do now is that I will rearrange them. Look at this. they have basically the same structure. So look, if we're going to have m is equal to a vel over v, for us to solve a, again, you guys can shift solve as much as you want, go ahead. For us to get a, we can put the v on top, we can put the vel at the bottom. We will have m dot v all over vel. So in this case, we will have, for a1, we will just have m dot times v1 all over vel1. Right? In this case, we will have 0.75. That was 0.297. That was from earlier. 0.75 kilograms per second times your v1, which is 0. What again? 1062. 1062 meter cube per kilogram divided by your velocity, which is your 20 meters per second. Very tame, right? Cancel, cancel. You'll have meter cube per second, and then there's a meter per second. So cancel, cancel. You will be left with meters squared, and then cancel, cancel. There it is. So before you write down or before you box an answer, note that this should be in cm squared. So if you're seeing that, hola, my answer is very small, that's quite fine. Okay, 0.75, 0.1062, 20. You will have an answer which is 3.9825 times 10 raised to negative 3 meters squared. So you're like, Allah, that's really small, right? I've been telling you guys to always check your units, right? To always check if the answer makes sense. Usually in my quizzes or in the problem sets, what you would do is you would round off to 2 decimal places. In this case, if you rounded this off to 2 decimal places, technically what you would get is 0.003. If you round that off to 2 decimal places, that is just a 0, which is not great, right? So usually just think maybe, right, either number one, there's something wrong with the computation wherein you're off by a factor of, I don't know, 10, 1000, that kind of thing. And in this case, the reason why it's so small is because you need it to be in cm. 1 meter is 100 centimeters. And again, for us to remove the rookie mistake, right? The rookie mistake in here is that you only apply this once. For us to do that, for us to do this properly, rather, you need to understand that this is meters squared. So you have to apply it 2 times. Cancel, cancel, cancel. You're now working with cm squared. And that basically means that your A1 in here is going to be 39.825 cm squared. Okay? So this is your A1. That's quite a small hole if you want to think about it. Right? And then your A2, I don't even have to look at the units anymore. Right? What I just need to do is A2 is equal to M times V2 all over vel2. And then what we will get in here is basically 0.75 times your vel2, which is 0.2275. There you go. And then your vel2, which is the astonishing, right, 895.8795. So there you go. What we will do is 0.75 times 0.2275, then 895.8795. Our answer in here is going to be 1.9045 times 10 raised to 4. 1.90455. So 9046 works. 10 raised to negative 4. This is now in meters squared. So again, what we will do is we will multiply it by 100 squared. Right? That is to fix the units. And now this is in 1.9046 square centimeter. That is now your A2. So notice that that really is a very tough nozzle, right? The A, right, was chopped down quite a lot, right? By 39.825. 1.9046. It was chopped down by a factor of what? 21, right? A1 over A2 is about 21. So that's a 21-fold decrease. So you're thinking, yeah, of course, the velocity will be much, much higher. Okay? So that is your problem 2, and I think that's it for part 2. That's it for part 2. Okay? So now we're done with pipes, nozzles, and diffusers. You guys, kayo na ang bahala, right? If you want to study problems at 5, go ahead. I think there's a diffuser problem in there somewhere, right? But now we will head into, oops, I pressed end again, right? We will head into, after this, we will head into, I actually forgot. Oh, right, mixing chambers and separators. Okay, so that will be the next part. That is actually also quite tedious, but we'll cross the bridge when we get there. Yeah, we'll cross the bridge when we get there. That's the correct code. Okay, I'll see you soon. Thank you.